So hi everyone. Here to talk about radiation fundamentals and specifically continuum emission today. I approached this talk with the idea that you're going to hear, some of you are going to be hearing some of this stuff for the first time, I'm sure. Each slide, well, not each and every slide, but many of these slides cover a topic that, for example, in the case of radiative transfer, that's a research topic that's spanned decades already. There is decades of research on it. One slide or a few slides in this talk is not going to capture all of that. The idea is to introduce you to the concepts and in some cases just bring them up so that in a couple of days' time when you hear a fuller lecture on the topic, you'll at least have heard some of the jargon or the keywords in there. So if something's not immediately obvious, hopefully it will be covered in more depth later, or you can go and research it on your own. That said, if something's not clear to you, please interrupt me and tell me, and I'll try and answer any questions you may have. So why are we here? Why are you here? You're here to use radio telescopes, presumably, and why do we want to do that? So we're trying to, through the use of radio telescopes, trying to establish a consistent system of measurement so that we can measure radiation intensity coming from astronomical objects. Sounds straightforward when you say it like that. Over the last 100 years-ish, century-ish, we've come to discover that radio waves coming from space actually come from many different sources, and there's different types of radio transmission, emission. A few examples of those. Obviously, there's radio emission coming from the sun. There was a solar flare last night. There's a lot of radio emission coming from the sun right now. H2 regions, Crab Nebula, supernova remnant. These all have different forms of how their emission is generated, measured. I'll be getting a little more into some of these, but yeah, basically the behavior of the emission as a function of frequency is what's changing here. I'll get into that a little bit. So just looking at any old radio source with our radio telescope, we tend to think in terms of flux density, where the source itself has some intrinsic luminosity that's radiated over 4 pi steradians, so solid angle, basically all directions in space. At least in our basic principle example. That luminosity is L, it's radiated over 4 pi r squared, a sphere, expanding into space. Then the intensity coming from that flux density is that flux density divided by the solid angle. In the simplest case, that source is radiating over its solid angle, which is 4 pi steradian. When you're receiving it at the telescope, then there's obviously a factor of how much solid angle your telescope is actually covering. And so when we measure a flux density of a source, we have to take that integral over the area of our dish. And this brings us to radiative transfer. So that source is emitting, and it's emitting photons. Those photons travel through space, and in this simple example, we have a cylinder of space that the photon is traveling through. And there's molecules in there, there's atoms in there, there's all kinds of things that can happen to a photon traveling through that space. Many of you will have heard of the Einstein coefficients, partition functions, and so on. So there's 3 main ways in which radiation is absorbed or stimulated. So the stimulated emission, if a particle passes near another particle, or a photon passes near a particle, it can stimulate that molecule, let's say, to emit another photon. There's just spontaneous emission. Molecules just out there will just change energy state and emit a photon. And then, of course, there's absorption as well. So your photon's happily traveling through space, hits a molecule, and that molecule absorbs the photon and dumps up in energy. So those 3 processes are generally captured by a partition function. But in this sort of more simplistic example, that's more spectral line emission, which Natalie may cover. But in this simple example, the change in intensity due to photons being absorbed or emitted through a section of space is due to the absorption of radiation, which we capture with this absorption coefficient, and that also includes the stimulated emission. And then the space itself is emitting some amount of radiation just from spontaneous emission. So the change in intensity over some distance traveled is the negative absorption coefficient because you're absorbing, plus the emission that happens along the way. So there's two simple cases here, just to hammer the point home. If that medium is only absorbing radiation, it's not emitting any of its own, you have the fractional change of intensity is equal to that absorption coefficient times the length of the path the ray is traveling. And then, so you can find that by just covering the integral. And if you want to find the optical depth of a path through space, you basically flip those limits and then integrate over that because the tau increases in the opposite direction. So then you find tau. This is our optical depth that you'll be hearing a lot about, depending on what frequency you're planning on observing at. Typically, it's non-zero. In a sort of weird case, when you have energy inversions, you get lasers, so you actually have an optical depth of less than zero. But in typical radio continuum observations, you have a tau that's some non-zero value, and if it's much higher than zero, basically if it's more than one, then your region is considered optically thick, meaning that you're not actually tracing your ray the whole way through it. Or if tau is much less than, these numbers are wrong. This should both be one. If tau is much less than one, then you're in an optically thin regime. So you're seeing most of the radiation that's coming from whatever your source is. In the second case, the medium can only emit radiation, it's not absorbing at all. And then we end up with this fractional change of intensity just being due to the emission coefficient times the length of the path. Which brings us to Kirchhoff's law. So if there's no change in intensity along the path your ray is traveling, then this whole change of intensity equals to zero, and then we can make this rearrangement of the equation. And then we can actually define then the intensity in this case is black body radiation, meaning there's no extra emission or absorption of the radiation traveling through that body. And what this actually means is that everything is in thermoelectric equilibrium. We usually call that local thermoelectric equilibrium. And in that case, we call that temperature the kinetic temperature. Well, it's equal to the kinetic temperature. The temperature of the body is equal to the kinetic temperature, which can be measured by spectral lines. So I'm just going to move water. So we know what the black body radiation is from other sources. Well, okay, I guess I'm skipping ahead. Before I get to that, the simplest solution of the radiative transfer equation is up here. We have some distance, at which we begin our ray's path, and then we are absorbing that by some amount related to the exponent of the negative optical depth. And then we have the source luminosity itself, the flux density, 1 minus e to the minus tau as well. So this covers the absorption and emission that happens along that ray path. And that gives us this source function. And as I kind of just covered, that source function is actually equivalent to the black body. And then, which is where I was skipping ahead to, where we have Planck's law, which just describes the black body. where we have no emission or absorption in some along our ray path. And some of you are probably fairly familiar with this. Planck derived this equation, well, didn't really derive this equation, it was a lucky guess in some senses. It can be derived. Planck didn't derive it himself. But yeah, if you know something about those Einstein statistics more than me, you can probably derive it. I don't know how to derive it, but it does come up in sentences occasionally. You may want to at least be aware of how it's done. Some of you are still waiting to take your defense. So yeah, you sometimes see a different, slightly different form of it depending on how you derive it. But you'll see this a lot. And it has a spectrum that looks like this up here, where basically the temperature of the black body moves that peak around in frequency, but typically has, you know, a sharp rise and then a tail falls away. And yeah, where that peak lies depends on the temperature of the source. We typically, or we often, take that Planck law and put it into the limit where h nu is much less than kt. That allows us to get rid of the exponent part of the equation and just simplify it. And this is the Rayleigh-Jeans approximation that's used a lot in radio astronomy. But especially for the GBT, this is potentially hazardous because we actually cover frequencies where this is not true and we cover temperatures where this is not true. So it's good to have a rough idea of where those limits are. So that I've just put up these two plots here that, you know, I'm saying you can consider h nu to be much less than kt at a factor of 10. So yeah, if h nu is less than 0.1 of kt, then you know, this is true. And you can see that this is true below 83 gigahertz if your source is 40 Kelvin. So 40 Kelvins depends what you're looking at. Right? If you're looking at a star forming region, 40 Kelvin, that's probably a little warm. If you're looking at an unknown boundary layer on an H2 region, that's actually very cold. So then just at 40 Kelvin, 83 gigahertz is your cutoff for the Rayleigh-Jeans approximation in a very rough sense. So if you're here to use Argus or something, you're out of that regime, and this may not be true. The other plot up here is I take 40 gigahertz as the standard, and then again say h nu is equal to 0.1 of kt. That gives you a temperature cutoff of 19 Kelvin, which is cold even for a lot of star forming regions. So yeah, if you're observing at 40 gigahertz and your source is warmer than 19 Kelvin, the Rayleigh-Jeans approximation does not hold. So, you know, what I've been talking about here is black bodies. Here, show you a few examples of how we actually use this in astrophysics. The sun is more or less a black body. You can see, is there a laser pointer? It's fine. There's stick. Great. So yeah, you can see some stuff up here. It's not particularly black body-like the sun. Slight excess of emission in the tail, and it's like lack of emission in the rising part of the spectrum. So yeah, so it's not a perfect black body, but it comes pretty close. And this is a black body at 5,777 Kelvin. We were just talking about the CMB. The CMB is a pretty good black body. Okay, here we go. Pentix and Wilson. What frequency was this at? It's okay, so it was about 3.5 gigahertz in relation to the last talk. And yeah, this black body, you can see these measurements are very good. These have large error bars at lower frequencies, but up here and around the peak, which is what we're normally trying to constrain, and that's probably why we get so many more measurements these days at higher frequencies, because they're trying to constrain this edge of the black body. But yeah, we have a 2.728 Kelvin black body. Now, black body radiation is what is referred to as thermal radiation, as well as just talking about the CMB. And that's how molecules act when they're at rest in equilibrium with their surroundings. So yeah, it's in some ways, and in the next talk, you'll probably hear a little bit about this. If you look at this black body spectrum of the sun, or not black body, the non-black body part of this spectrum, you can see there's lots and lots of little peaks. And in some senses, you can imagine a black body just consisting of like many spectral line emissions all blended together. So that said, there are other non-thermal ways of producing radiation that we measure in Continuum. And basically that's always from accelerating a charge, which these are all covered by the blanket term Bremsstrahlung radiation, though that's often used exclusively to denote free emission. It actually covers all of these. Here's an example here in this GIF where a molecule is coming along, which, an electron is passing by a nucleus, a charged nucleus, and is changed in direction by passing within the magnetic and electric field of that nucleus. And change in energy means energy must be conserved, a photon has to be released. And there's many examples of this in the universe. So there's planetary nebulae, H2 regions. These are all very hot. Well, most of these are very hot. Around an H2 region, you have an ionized boundary layer that's probably at 10,000 Kelvin, give or take. And these all emit free emission. There's magnetic field acceleration of the charge. So you get spiraling electrons around the magnetic field line, or ions. And in the relativistic case, that's synchrotron radiation. In the non-relativistic case, that's cyclotron. And there's beta decay, but I don't know much about that. Cool. There's other, so synchrotron radiation, you see it around AGN, you can see it in the sun. Well, these more, a lot of these are sunspots, so there's magnetic field lines coming in and out of the surface of the sun there. Accelerating charges, and then this is basically a map of the magnetic field of the Milky Way. So back to the form of this radiation and basically the frequency spectrum of this radiation. In the free case, you have a curve that looks like that, sort of the lower end of a black body. Depending on frequency or wavelength. This is how synchrotron radiation appears, and then this is how general thermal radiation appears for any given source. I mean, that slope changes somewhat with the individual source. But this is a very basic idea of how that changes. And so if you were to measure any particular source, you could tell what kind of radiation is coming from it simply by measuring its intensity at multiple wavelengths. Of course, these processes tend to be blended together. And here we have a far infrared and radio spectrum of M82, which is a kind of typical galaxy. You can see that the three lines kind of get blended together because all of those processes are happening at the same time. So that's sort of the main part of, that's a very whirlwind trip through continuum emission at radio wavelengths and the basic astrophysics behind it. You'll probably be hearing some more about that later on. Now I was going to bring up some issues that directly relate to observing itself and the use of the telescope. I'm going to be cutting this short fairly. I'm going to be cutting this talk fairly short. I was slotted for an hour, but it's more of a half-hour talk, so it's lots of time for discussion. But something you're going to come across if you do any continuum observing is 1/f noise, or sometimes called pink noise, sometimes called flicker noise, but I don't think flicker noise is specifically this, but it's still called that sometimes by some authors. Something to be aware of. The traditional radiometer equation, when you're figuring out how much time you need on a telescope, you use this equation. Basically, your bandwidth times your integration time, the inverse of that square rooted, gives you an estimate of the noise, the sensitivity of your observation. So yeah, this standard deviation in the TA I'm calling noise. That's basically your sensitivity. If you've used the sensitivity calculator of the GBT, that's usually what you're calculating. The system temperature is unique to the receiver, the weather, other factors. And then, yeah, as I said, your bandwidth and integration time. The more bandwidth you have, the more sensitivity you'll get. The more integration time you use, the more sensitivity you'll get. Now, that's valid for spectral line observations because you're getting rid of your 1/f noise, usually just through base. The problem is when you're not doing baseline subtraction, i.e. you want to measure the total power coming into your telescope, you're measuring the continuum level, you get gain fluctuations that act as a 1/f contribution to the noise. And you can see the behaviors of these types of noise. So this is white noise, just essentially random. You have a Gaussian form around a mean. But the 1/f noise doesn't behave like that. The gain fluctuates and it's not as predictable. So over time, your noise actually gets slightly worse. And then, yeah, so you end up with this contribution to your sensitivity, where, yeah, your gain is a function of time, essentially. It's actually 1/2 the time because your whatever your bandwidth is, you get a higher contribution at the lower frequencies. So you actually need to integrate over a shorter amount of time. Not very clear. Dave is going to cover this in more detail in a following lecture. Okay, this slide is more or less covering, well, that top part is kind of covering what I just said, where the 1/f noise is removed in baseline subtraction from spectral line data. And you can see, yeah, again, that this is, I mean, I don't know how scientific this is. This is a GIF of white noise versus pink noise, supposedly. I'm believing Wikipedia when they tell me that. And you can see that there's more sponge structure, less randomness to 1/f noise, which is why you can't just get rid of it as easily. But we can counter it through some clever observing techniques, and some that aren't that clever even. Fast switching is a good way of doing it, taking a lot of short observations and then adding them all together at the end. Yeah, there's some other techniques that you can use, but that's sort of the expert level. One thing you'll see, so, you know, the thing about 1/f noise is it goes down as 1/f, so there's a slope on a frequency spectrum, whereas broadband noise, white noise, just basically stays the same over frequency. It's f to the 0 power, whereas 1/f is f to the -1. And so there's a corner frequency where those things meet, and the longer you integrate, you know, this is going to go down. The white noise goes away the longer you integrate. Whereas this actually goes up. So this corner frequency moves around depending on your integration time as well. So this is something you need to be aware of when you're proposing to do a continuum modulation with the GBT. At some point, you're going to hit the 1/f noise, and it's probably going to be sooner than you think. A lot of people leave it out. Like, you know, a lot of times the radiometer equation doesn't even include the contribution. So you might naively propose for the GBT and just use that equation and say, I can get this sensitivity, but it turns out you're going to hit the 1/f noise, you actually can't reach the sensitivity you want. So you need to be aware of it and look into that before we actually do the proposal. Something else you may not be as aware of is confusion. A lot of continuum observations are confusion limited, which means that there's so much radio emission across the sky that you're trying to look at your source, but in fact you're just picking up emission from other sources. This is an image of a Lockman Hole, and this is not noise. These are all galaxies. Right? So you can imagine trying to look at a given source in that field, and depending on the size of your beam, you know, you're going to be picking up a bunch of other sources too. And if they're brighter than the source you're trying to look at, then you're kind of out of luck. Unless you can somehow model that emission and subtract it. So yeah, when you are trying to detect a target source, you need to be aware of how bright that source is above the average background, and if this is your average background, you know, give you some idea of what you're up against. And then if you are lucky enough to have a fairly isolated source, you know, maybe there's a, you know, your source is here, and there's this sort of less bright region around it, then maybe you can isolate your source that way. And that gets better the higher in frequency you go because of this thermal. Well, I guess, but yeah, the higher in frequency you go, the lower the confusion goes. I'm gonna think about that one before I say that again. Right, so that was very quick, covered a lot of ground. Do you have any questions? I'm happy to answer them.
So the source of gain noise is just the variation of gain of the telescope?
Yeah, I mean, all noise is, comes from fluctuations in instrumentation, fluctuations in voltages. Yeah, the one over F noise is typically a gain fluctuations, total power fluctuations.
And to get the total noise density against frequency plot that you show, where is any? That one.
Yeah.
You just not need to make a study of how the gain varies through time, and you get that plot.
Yeah, so you basically can just set up your telescope to take many, many short integrations, and then as you sum those, your noise will go down. But then you'll see this behavior.
Okay, and that plot doesn't change through time, like usual.
Well, as I was saying, so the longer you integrate, the white noise will decrease as you stack integrations. But this noise will actually go up. So this line will actually move to the right, and this will come down.
Okay.
The longer you integrate.
And you should repeat this kind of study every, I don't know, couple of months, couple of years.
Well, I mean, it's a fairly well, it should be a fairly well established number for a given receiver. So we have a memo internally that you can probably access. And certainly go to your project friend and they'll be able to give it to you. But we've measured this for each and every receiver. Well, I think every receiver, most of our receivers. So for all of our receivers, we know what this is. And is it in our observer's guide or proposer's guide? It should be, but
we reference it. It's GBT number 282.
Right. But yeah, so I don't know if the actual values are in our proposer's guide, but you can access the values. So the way we've established it is actually there's a given bandwidth that is where that's the bandwidth at which the 1 over F noise will be equal to some sort of threshold. And so you can figure out what kind of bandwidth you can use and how quickly you'll hit the 1 over F noise if you're trying to do a continuum measurement. And some of our receivers are much better than others. So our Ka band receiver is easily our best continuum receiver. Well, there's a Mustang, but certainly below Mustang 2, the Ka receiver can do a much broader bandwidth observation than any of our others. Any other questions?
Can you go back to the slide where you introduced the radiative transfer equation?
This one?
The one before Kirchhoff's law. Yeah. Are there any practical examples where emissivity or absorption coefficients are actually close to zero?
Or absorption coefficients close to zero. Well, I mean, that's basically free space. So, I mean, if you're looking through the interstellar medium, there's nearly always some absorption. And so basically the optical depth is zero. I mean, this is how the Lockman hole was discovered, because Jay Lockman was, I don't think he's in the room, but he was in a lecture and somebody said there is no part of the sky that has an optical depth of zero. And he went and looked for it. And the Lockman hole is still today the lowest column density we know from Earth. So yeah, whichever direction you look in, there's something. I can't think of. I mean, the only counterexample to that really is like amazing medium, where you're getting more out than you put in. Yeah, that's also a sort of special physical case, right?
And are there any exclusive cases that only absorb, like the case one? And then those that only vomit?
Well, thing is, if something only absorbs, then it must increase in temperature, right? Like, so you end up with the ultraviolet catastrophe. Yeah, you just end up having something that just got hotter and hotter and hotter. You see that. I mean, it may be maybe on short time scales. Something like that exists. I'm not thinking of any right now. Yeah, is there any other questions? Anything online?
Nothing online right now.